this is the final CHUMP build, a 4-bit TTL processor. Unfortunately, the circuit doesn't work due to a few wiring issues, but in terms of how it works, the clock source, the triangles on the sides of the chips are built using 555 timers and a combinational circuit, generating timing signals essential for synchronizing operations. The clock pulse triggers updates in the program counter, address register, and accumulator, driving the sequential steps of computation. The program counter increments with each clock pulse, feeding its output into the program ROM, which translates the counter value into specific instructions. These instructions are divided into operation codes, opcodes, sent to the control ROM, and constants sent to the multiplexer. The program ROM essentially guides the processor through its operational steps. The multiplexer selects between two data sources, constants from the program ROM or data retrieved from RAM. This selection depends on the opcode and control signals, ensuring the correct values are used for operations. The selected data is routed to the ALU, program counter, and address register. The ALU is the processor's computational core, performing arithmetic and logical operations based on control ROM instructions. It processes input data from the accumulator and the multiplexer, producing results sent back to the accumulator or RAM. The accumulator temporarily stores the output of the ALU, acting as a working register for ongoing calculations. Its output is fed back into the ALU and also into the RAM's data input pins for storage when needed. The address register stores memory addresses for data retrieval and storage. It receives data from the multiplexer and updates on each clock pulse. Its output is connected to the RAM's address pins. The RAM chip serves as the computer's main memory, holding both data and instructions. It has dedicated address and data input pins with read and write operations controlled by the control ROM's opcodes. Also note that the outputs from RAM are inverted through a NOT gate. The control ROM interprets opcodes from the program ROM and issues control signals to the ALU, accumulator, address register, and multiplexer. This coordination allows the processor to execute instructions like load, add, subtract, store, read, and conditional jumps such as if 0 and go to. Unfortunately, my code is unable to be displayed in my CHUMP, but this is what the code would do if it were to be displayed on my CHUMP. Essentially, it calculates the Fibonacci numbers by adding the previous two values from memory and updating mem0 and mem1 with the latest results. So first we read address 0, and there's a 0 there, and then we load it to the accumulator, and you read address 1, and then you add that to the accumulator, and then you store that accumulator value to address 2, and then you read address 0 again, you load that to the accumulator, read address 1, and then you add that to the accumulator, and then you store that to address 0, and then you read address 1, load that to the accumulator, read address 0, and then add that to the accumulator, and then store that to address 1, and then start from the beginning again. And this just continues. This is just a code to program the control and program EPROMs. It's a variation of the code from the second video of the CHUMP series, but there is just a new array for the control codes. Thanks for watching.